Lecture number 20, Rearrangements of the Ideal Gas Law. So last time, excuse me, we talked about the ideal gas law and how we can rearrange it under changing conditions so that we can relate pressure, volume, number of moles, and the temperature to each other of any gas, what we're assuming is an ideal gas, at any time, right? Or under a variety of situations. Today we're going to talk about a couple of other rearrangements to give us some additional information, but also then expanding from a single gas to multiple gases, and then finally we're going to tie this into the sort of larger stoichiometry. So let's look at these two other rearrangements. So we can include the density, with density being some mass divided by some volume in this. So we can take, of a gas, we can take the pressure times the molar mass of that gas would be divided by the gas constant times the temperature would give us the density. The density here is going to be in grams per liter, as opposed to most liquid solutions that we have is grams per milliliter. But all these gases, fewer moles or amounts per volume, we're going to go to a different unit of grams per milliliter. So we can either talk about either density or we can talk about the molar mass, rearranging these two, where the molar mass of a gas is going to be the density of that gas times the gas constant times temperature divided by pressure. Again, all of these depend on the gas, so we're going to just a further sort of rearrangement of the ideal gas equation, where now we're including this molar mass instead of the number of moles. We can then expand this to talk about, instead of a single gas molecule, we can talk about a mixture of gases. In these ideal gases, because we said that those molecules don't interact, we can sort of assume or treat each gas independently, assuming it's going to take the entire volume. So then the total pressure is going to be the sum of each one of those pressures developed or created by each of those gases. Which brings us to this law of Dalton, or Dalton's law of partial pressure, which is the total pressure of a system, of a mixture of gases, the sum of the pressures that each would exert if it was present alone. So we can treat each gas individually, saying, okay, we have this gas at a certain quantity. Treat the second sample of gas, again, its amount, see how much pressure it is, and then the total pressure is just going to be those two numbers combined, or the P total is the pressure of one gas plus the pressure of the second, and so on. So this allows us to take a mixture, a fairly complicated mixture, and simplify it into this same PV equals nRT equation. So if we look at a mixture of gases here of A and B, of some volume V, we can say that the pressure of gas A is going to be the number of moles of gas A times the gas constant times the temperature that exists divided by the volume. Right? And the pressure of gas B is going to be the number of moles of B, again, times the gas constant times the temperature divided by the volume. So now we have those two values. Right? So that the total pressure is going to be the pressure of A plus the pressure of B. But we can also say that this pressure is coming for some fraction of the total. So we can include this new value, what we call the mole fraction here. It's the number of moles of A divided by the total number of moles. That would be the mole fraction of A. So we can then say that the pressure exerted by A is going to be whatever fraction of the total that is, that mole fraction of A, times the total pressure. We can do the same for B. So for any gas in a mixture, the pressure, individual partial pressure, is going to be the mole fraction of that gas times the total pressure. Right? So we can sort of treat these gases individually, or we can talk about them in the whole. Either way, we can sort of move between and get information about each individual gas. So that's sort of straightforward, but where it plays out most is when we're collecting a gas. Right? So we're doing a chemical reaction, we produce a gas. If we want to have information about that gas, we need to collect it. And the easiest way for us to collect it is to put it into a container that already is full, push out whatever was there before, and include that gas. Now inside that container we're going to have a mixture. So let's look at this. So let's say we have potassium chlorate, and we're going to decompose it. Right? We're going to add heat. It's going to break apart into potassium chloride and oxygen gas. Right? We're interested in how much oxygen gas is produced, So what we're going to do is we're going to collect that by the displacement of water. So we're going to heat up, create this oxygen gas. It's going to flow in here into this container, and that gas is going to displace the water. Well, water is sort of volatile, so there is some water vapor that's present above any water solution. So now at the end in this container, we're going to have not only oxygen gas, but we're going to have some remaining water vapor. So in that, the total pressure that that cylinder contains is going to be a mixture of both the oxygen gas and the water vapor. So if we have fairly good information about the vapor pressure, the amount of water that exists as a gas under a variety of temperatures. If we know what temperature we're operating at, we can then calculate this or determine the partial pressure of the water, and then the pressure of the O2 is just going to be the total pressure minus that. Right? So that's one of the ways that we would use this type of Dalton's law of partial pressures. The last thing we're going to talk about is now we can talk about the amount of gas, not only because it's directly related to the amount of gases, gives us some other information. We can add this to our stoichiometry. So we can now talk about, in our starting material, we have some amount, either grams, a concentration, or now some volume or pressure. Right? Then we can, based on what it is, we can either, if it's a mass, we can convert to moles. Now because of the ideal gas law, we can then convert either a volume or a pressure to the number of moles. Right? In this balanced equation, then we can go from moles of one to moles of the other, and then worry about the final product as we're showing up here. Right, so let's look at one of these examples. So let's look at the volume of CO2 produced at 37 degrees Celsius and 1 atmosphere when 5.60 grams of glucose is used in the following reactions. We're taking glucose in the presence of oxygen to get to carbon dioxide and water. This, remember, is a combustion reaction. It's a redox reaction. So the amount of carbon dioxide that we produce is going to be directly related to the amount of glucose that we consume or decompose. Right? So we're going to go, in general, we're going to go from the grams of glucose to the moles of glucose. Using the molar ratio, we'll go to the moles of carbon dioxide, and finally to the volume of carbon dioxide. So if we look here, we have the 5.6 grams of glucose. Convert to moles using the molar mass. We have 1 mole is 180.16 grams of glucose. The molar ratio between carbon dioxide and glucose, we get 6 carbon dioxides for every 1 glucose that's formed. So we end up with forming 0.1865 moles of carbon dioxide. Right? That's a gas, so we can talk about its volume using PV equals nRT, where we take that number of moles, 0.1865 moles, times the gas constant, 0.08206 liters atmosphere divided by Kelvin mole, and that temperature in Kelvin, 310.15, divide by the pressure, the 1 atmosphere, and that gives us a volume of 4.75 liters. Right? So what we've done is now just added an additional step we can take in our stoichiometry. Now we have grams, we have moles, we have concentrations, now we have this idea of gases. And all of these steps we're starting with some amount at the beginning, going to moles, mole-to-mole ratio, and then from moles to whatever quantity amount we want at the end, be that grams, concentration, or now volume or pressure for a gas.
I don't get